I'm Michael Coblenz. Today I'm going to tell you about Pliers, a process that integrates user-centered methods into programming language design. As you can see from recent major bugs, these are 3 just in the past few months, it's still far too hard to write software. Log4j was due to a code injection vulnerability, forced entry was caused by integer overflow, and a bug shut down Amazon Web Services for the better part of a day. Part of the problem is that programming languages make it too easy for programmers to accidentally insert bugs. Suppose you're programming in an object-oriented programming language, and you want to call foo on x. But it's not safe to do that if x's type doesn't implement foo, and you might have a hard time checking if you're not using a statically typed language. You also can't invoke foo safely if x might be null, or if x might be a reference to freed memory. Likewise, suppose you want to call setAddress on a person reference, but what if person references an object that's used as a key in a hash table? Mutating that object could corrupt the hash table. In this work, we view programming languages as user interfaces that programmers use to achieve their objectives. Our goal in this work is to enable language designers to create languages that make programmers more effective by taking user needs into account directly. We choose safety properties that are relevant to users, and then design languages that provide those properties as effectively as possible. Then we evaluate to see whether we succeeded. The goal might be fewer bugs when doing a task, or task completion in less time, or making it more likely to complete a task correctly in a certain amount of time. Or it might be to enable people to do the task with less training than what was previously required. Pliers, which stands for Programming Language Iterative Evaluation and Refinement System, is a systematic method for making languages effective for programmers, while at the same time retaining key safety properties. In a user-centered way, Pliers involves users throughout the design process. We use Pliers to develop and show benefits of 2 different languages. Pliers includes 5 steps. First, we analyze the programmer's needs using methods such as interviews, corpus studies, or contextual inquiry. This leads us to develop some initial ideas for the language, which we call a conception. These ideas include a formal aspect, such as a core calculus, and formal properties that we would like the language to have. We might also sketch proofs of those properties to become more confident that the language will actually have the desired properties. There's also a user-centered aspect in which we design example programs and maybe implement an interpreter or compiler. Now, it's impractical to do user studies for every design decision. In order to focus our user studies, we do a risk analysis using techniques such as cognitive dimensions of notations or a comparison with prior systems to see which aspects are worth studying in more detail. Then, once we've identified key usability risks, we iterate on the design in a typical HCI fashion. We evaluate the system either with user-centered methods or with traditional methods, such as performance testing, and then change the theory and the prototype accordingly. Finally, we do a summative evaluation to see whether we have achieved the goals we set out for the language. One project concerns blockchain programming. Blockchains are used for high-stakes applications in which the users don't trust each other. On these systems, it's particularly important to get the programs right the first time, since money can be stolen from vulnerable contracts very quickly. We've seen millions of dollars stolen through vulnerabilities that were caused, in part, by traps laid in the Solidity language, which is commonly used for writing smart contracts. We made 2 observations about blockchain applications. First, they typically manage important assets such as virtual currencies. If an asset gets trapped inside a smart contract, the money is lost forever. Second, which operations smart contracts support frequently depends on the contract state. The DAO hack, for example, involved invocation when the contract was in an inconsistent state. In our language design, we used a technique called linearity to ensure that assets cannot get lost inside contracts. And we used a technique called typestate to enable the compiler to reason about which operations are valid according to a contract state. This is a new combination of features in a programming language, and user studies hadn't evaluated the usability of either technique. Now, we were interested in obtaining formative data on the usability of our design. A traditional way might have been to implement the language, develop training materials, and then do a usability study. But implementing languages and teaching them is a very high-cost effort. We were interested in obtaining formative data early so we could refine the design before implementing it. To obtain earlier stage usability data, we adapted the Wizard of Oz technique from HCI. We gave users a text editor and had an experimenter simulate error messages that a compiler might have generated. We also wanted to avoid teaching participants a whole new language. Why? Well, teaching a new language can take a long time. And suppose that we did teach participants a new language, and then we observed that they encountered a problem doing a task. The problem could have been caused by any aspect of the design, rather than the specific design decision we were trying to assess. To address this problem, we adapted the design questions we were interested in to a language for which we could find existing programmers. In our case, that was Java. Now, one key aspect of Obsidian's design is that the types can actually change as a result of operations that occur. So what did we find? The studies enabled us to identify and address a collection of usability problems. For example, although concise syntax is traditional, we found that a more explicit verbose syntax helped clarify changes in types that occur to method parameters. Also, although type annotations normally provide complete type information, we found that for local variables, they should actually be incomplete, because otherwise they could be confused with state restrictions. This led to adding a new language feature to allow people to assert type state at arbitrary points in the code. To see whether Obsidian was better than Solidity, we ran a randomized controlled trial. We recruited 20 Java programmers. We assigned half of them to use Obsidian and half to use Solidity. We gave them a tutorial, which took about 90 minutes to complete. Then we gave them 3 programming tasks. The Obsidian participants completed significantly more tasks correctly than the Solidity participants did, 1.5 versus only a half. Now, what are some implications for other kinds of work? First, it's important to remember that tools for experts, such as programming languages, benefit from usability studies too. Experts are people and deserve tools that take their needs into account. Second, the HCI methods we used required a relatively small amount of adaptation, so this kind of work could be undertaken by many HCI researchers. One observation was that the think aloud method requires probing to really understand what challenges people encounter. Also, our technique of adapting research questions to familiar experimental settings, in our case Java, helped us focus our studies and made them much more feasible. This approach may be useful in other contexts as well. In conclusion, Pliers is a user-centered design process for programming languages that incorporates qualitative, quantitative, and formal methods. Pliers can lead to better programming languages which result in safer users. Thank you very much.